I've given a bunch of simple examples of tail recursive functions. I'm going to give one more example of a tail recursive function and then show you a different kind of style of recursion. So I'm going to start with the reverse function. We all know what the reverse function does because it's really intuitive. It just flips the order of the things in the list. It doesn't matter what's in the list. You can flip the order of things without having to care what the things are. So reverse has a polymorphic type. It takes a list of anything you like and flips the order and gives you back a list of the same type with the order reversed. Okay? Reversing the empty list is the base case. What's the reverse of the empty list? You can't put anything in it, so it has to be the empty list. If you reverse a non-empty list, it's going to be a bit like this property that we did over here. We're going to try and work out how to reverse the bigger list by reversing the slightly smaller list. So how do we do that? Well, we take this element. If we've reversed the rest of the list, let's take this example. If we've reversed the list 2, 3, how do we combine that with the element 4 to get the thing that we want? Sorry, stupid. 2, 4 is the example. We've reversed this list. How do we combine the first element 1 with this list to get this list? Well, we need to put the 1 on the far end of this list. And how do we do that? Well, we just saw how to do that in the previous example. We put it into a little baby list and stick it on the end. Okay? So what we've done is we've reversed this and then we've put the first element on the far end and we've got the same result. Okay? Any questions? Oh. Sorry, Mike. All right, so I've put in brackets here, this is inefficient. So why is that? Well, to understand why it's inefficient, let's define the append function. That's this guy. But let's define it not as a symbol, not as an operator, but as a function of 2 arguments. We'll do the same job. It takes a list of things, another list of things, and gives us back a list of the things all combined. I'm going to define it with recursion. And the way that I'm going to solve this is by doing recursion on the first argument. That is to say, I'm going to step by step I'm going to try and work my way to the end of this first argument. Because when I get to the base case, that's when the first argument is empty and the second argument is some list, then the answer is that second argument. So these are the 2 cases. So this is actually a little bit different because it's a 2-argument function, and the recursion I'm going to do sort of in the first argument. So if I want to append a list of one thing followed by other things onto some other list, let's assume that I know how to append x's onto y's. What do I do to build the result that I want? Well, I'm just missing this one element. Where do I put that one element? Well, I put it at the front. So the append function is pretty straightforward. If I can remember how to spell it. And there we have it. So why was reverse inefficient? Well, how many steps does it take to append 2 things together? Well, it depends how long the first argument is. If I have a really long first argument, I say 1,000 elements, then it's going to take me 1,000 recursive steps until I get to the end of that first list. And then when I get to the end of that first list, the answer is the second list. So the number of steps it takes to do an append operation is roughly proportional to the length of the first argument, right? If I give a big first argument, that's how many steps the append function will need to take until it gets to the base case. If I have a small first argument, then it finishes straight away. The argument is the second argument. Okay? So the number of steps for append is proportional to the length of the first argument. So the number of steps we need to do to compute the reverse is the length of this in order to compute the append. So that's if the initial list is size n, that takes n minus 1 steps. And then we go, and then that's even before we've computed, sorry, that takes n minus 1 steps, and then we do the recursion. So on every step of the recursion, step 1, we take n minus 1 steps to compute the append operation. The next step, we take n minus 2. The step after that, we take n minus 3. So if we add all those up together, what do we get? If we take n minus 1 and add n minus 2, n minus 3, n minus 4, what do we get? Roughly. It's something like n squared, right? So it's quadratic. So now we're talking about a seriously a big increase in the number of steps if we have a big list. That's why I say it's an inefficient reverse function. How do we do it efficiently? Well, let me go and show you some slides that will, I think, hopefully explain that. So let's imagine that this is our list here. So I've written it. It's a list of flower pots, okay, and they're all different colors. And I want to reverse this guy. So imagine this list as a stack of flower pots like this. And why have I written it as a stack? Well, because it kind of reminds you that doing stuff at the top here, at the front of the list, is a lot easier than doing stuff down at the bottom. So if I want to do stuff down at the bottom, I have to kind of unstack them all and restack them. So taking the first element is easy. Pull out the top flower pot. Whereas doing stuff at the other end, taking the last one, is harder because I need to take out all the flower pots until I get to the last one. So that's a bit like the way lists work. That's why they're kind of a bit asymmetric. It's easy to do things at the top and harder to do things at the bottom. So if you were going to reverse this list, and imagine the list is actually this stack of flower pots. I want to reverse this stack of flower pots. How would you do it? Well, what you would do is that you would create a space to reverse this. You would make enough room over here on the right to reverse it. You would reverse them into an empty space. So you take the first flower pot and you put it down in the new empty space. And then you take the next flower pot and you would put it on the top of that, on the front of that list. And you take the next one and put it on the front of that. And you take the last one and put it on the front, and then you'd be done. The thing you have on the right is the reverse of the thing you started with. How many steps did that take? It took 1 step for every flower pot. Roughly n steps, not n squared steps. So that was way more efficient than the recursive method that I just described. So how can we represent this method as a recursive function? So the way we're going to do that is think of the same process as the process of starting not with 1 list, but with 2 lists. So imagine instead of having just 1 list, the thing you want to reverse, you had 2 lists, the thing you wanted to reverse, and the empty list. Okay? So this is the place where we're going to build the result. So now we can build the result by taking the first element and putting it, instead of at the front of what we get by reversing the rest, we put it just at the front of this empty list. That's easy and cheap. And then we just carry on. Put that one on the front, that one on the front, that one on the front, and then we're done. Okay, so that's the strategy. Instead of starting with one list, we'll start with two lists where one of them is empty. Okay, so but how do we do that? We're trying to define a function. So I'm going to call it reverse. Let's call it reverse double prime. This is going to be the efficient one. I'm trying to define a function to reverse a list, and I'm saying, but if only I had two lists where one of them was empty, then I could do it. That's not a problem. We just create another function. We're going to call it a helper function. The helper function will have two lists, just like we need. So to reverse the list x's, I'm going to use a helper function. I'm going to call it rev. And rev will just be do the job I want, except rev will start with not only the list I want to reverse, but a place that I can stack the flower pots to build the list that I want. All I need to do now is define my helper function for reversing into a space. So to define this, I have to define what this function will do, not just when this list is empty, but at any step in the process. Okay? So it's when I have x's and y's, what do I do? Well, the base case, when are you done? That's when the list you're trying to reverse is empty. Okay? The upper stack is empty. That's the base case. The base case is when the first argument is empty. And what's the result? The result is the second argument. Okay, so we've finished reversing. The recursion case is where we reverse a list that is not empty. And what do we do in that case? Well, we take the thing off the front of one list and we just put it on the front of the other list, just like we did in the illustration. And when we've done that, what do we do next? Well, then we carry on with the same process. We reverse what we get, but after we've taken the element off the first list and put that element on the front of the second list. So we've defined the reverse function using a helper function that had a little bit of extra space. And the method that we used was just like the one that we illustrated on the slides. At each step of the recursion, we take an element off the front of the first list and put it on the front of the second list and carry on with the same process until the first list is empty. Then we know that the result will be there waiting for us in the second list. So this style of recursion is called tail recursion. And it's very common that we use a helper function to do that. But because this function is actually not the function we're interested in, this one is the function we're interested in. What we typically do when we define a helper function is to make this function invisible to the rest of the program. This is a kind of private function of this guy. And how do we do that? How do we sort of make this function invisible to the rest of the program? We don't want to use this function. This is the only guy who should use this function. We make it a local definition. So a local definition in Haskell is defined by using a where, and then we define this by indenting this definition one or more spaces. I'll do a few spaces and lining them all up. So now this definition is inside of this definition. Let me just compile it, make sure I haven't done anything wrong. If I ask what's the type of reverse double prime, our fast reverse function, it's the type we expect. If I ask what's the type of rev, it says, never heard of it. Don't know what you're talking about. The only person who knows about rev it's only visible to this function. And that's because it's a helper function that only really is used by this function.